We're on to Chapter 8, and we're going to first talk about Section 8.1, Molecular Compounds. Okay, here's some Tinker Toys. I don't know if you remember those growing up. I do. Okay, and we have basically sticks and little square pegs that we can put things into, and we can make a nice structure. We kind of looks like something we had for the ionic compounds before. But you can make a lot of different toys with these Tinker blocks. So, what does a molecular formula tell us? Well, any kind of formula tells us what the elements are that make up the compound, okay, and the relative ratios of each of the elements to each other. So for one molecule, it would tell you, for instance, if it was something like H2O, okay, so let's look at H2O. If we had H2O, that's water, so hydrogen and oxygen are our elements. And this too refers to two hydrogens. So there's two hydrogens per oxygen. Okay, there's another compound called H2O2 called peroxide. If you ever had a cut, you may have got this put on. It burns a little bit. Now this is unusual because we have the 2,2. Usually we would reduce that, but we have two hydrogens per two oxygen. So hydrogen peroxide, hydrogen peroxide. That's where the name comes from. Okay, now in nature, the noble gases do not form compounds. They're very, 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 very stable as they are. I told you they're a little snooty. They don't want to form anything else, and they're monatomic, meaning that you'll find them in nature as single atoms, okay? And helium is very light, okay, compared to air, so it floats. So a couple of the noble gases are much lighter, helium and neon, than air, so balloons filled with them will float. The other noble gases are heavier, and they'll just sink. But there are some elements that are not monatomic. Something like oxygen, you won't find O floating around in nature. What we breathe in is O2. Okay? There's two atoms of oxygen that are combined into a molecule of oxygen gas. If you're a scuba diver, however, you're going to breathe compressed air. Pure oxygen is not a good idea for a scuba diver. Okay, we saw in the last chapter that ionic compounds form crystalline solids with very high melting points. However, covalent compounds usually have much lower melting points and very different properties. We went over some of the properties of ionic compounds and metallic compounds. We're going to see different properties for the molecular compounds or covalent compounds. Okay, we know that water, for instance, is liquid at room temperature, and we know that carbon dioxide is a gas at room temperature. And nitrous oxide is something that you might get at the dentist office sometimes. This gives you the gas to calm you down. It's actually laughing gas, too, if they give you too much of it. Okay? So carbon dioxide and nitrous oxide are both gases at room temperature. Okay, so they're definitely not ionic compounds because we don't have a transfer of electrons. Okay? They're doing something else. What is it they're doing? They're actually sharing electrons. Okay, ionic bonds actually, one gives up the electron, the metal gives up the electron, and the non-metal will then basically accept the electrons. Any other atoms combine by sharing electrons, and they share, instead of an ionic bond, they have what we call a covalent bond. Oops. Okay, let's get the pen. So covalent bond is a sharing of electrons. Very important. So molecules, okay, just like ionic compounds were neutral, when we bond things covalently, they are also neutral. Okay, so any compound, whether it be ionic, molecular, covalent, however we want to say it, any compound is going to be a neutral group of atoms chemically combined, okay? So they're joined together. Oxygen consists of oxygen molecules. Each oxygen molecule consists of oxygen bonded to another oxygen. So if we wanted to do that, oops. We could just draw it this way, like that, okay? But we'll also learn how to do Lewis structures for these two. Okay, there are several elements that are like oxygen. They'll form what's called a diatomic molecule. Okay, di means two, so two atoms in the molecule. Okay, so I'll give you a very easy way to remember this. There's two ways. One is called Brinkelhoff. So we have bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. There's 7 of them. Now, I'll also show you something that's really kind of cool. Let me go to the periodic table. And I call it the 7-1 rule. So here's element 7. Okay, so we start at element 7, and I'm going to change this to my pen. Let me see if I can do that. Let me go over here. Okay, so we have our
Lorenzo
7.
BRZ, if you are upstairs in the upper academy, Lorenzo, please report downstairs
All right.
to the elementary school office.
That looks like
Lorenzo,
a 7.
please report
So what did I
downstairs.
do?
Thank you.
I went to element 7, went all the ways to group 17 or group 7A, stopped, and went down to iodine. Iodine looks like the Roman numeral 1, okay, which says, oh, I have to go over to Arabic numeral 1. So 7, 1. 7 to 1 to 1. 7-1 rule. NOF, Cl, Bri, and H. Same as Brinkelhoff. So there's 2 ways of remembering that. Okay, whichever one is easier for you. If you're a visual person, use the periodic table. If you like a little name, use Brinkelhoff. Okay, molecule can also be made of atoms of different elements. So we talked about water already. These are called molecular compounds. Sometimes we call them covalent compounds. A molecular formula is the chemical formula of a molecular compound. So a molecular formula, okay, is instead of an ionic formula or a formula unit, it's a molecular formula. Okay, so H2O would be a molecular formula. Okay, in general, how many atoms of each element a substance contains? So there's water. We have the 2, as I mentioned before, is written over here. That corresponds to that. Okay, and if we only have 1, of course, we don't write the subscript. Butane is another molecular compound. It contains carbon and hydrogen. Okay, it's called butane because there's 4 carbons, and butane is a prefix that means 4, and the ane is going to tell us that it has only carbon and hydrogen in it. So there's 4 carbons for every 10 hydrogens. Okay, looks like they're making some sort of creme brulee, or maybe it's a Portuguese pasta de nata. Okay, representing molecules. Okay, the subscripts are not necessarily the lowest whole number ratios. Okay, they basically are ratios, but you could have a compound that has, let's say, C2H4, and you could have a compound that's C4H8, and they are two different compounds, and they both have the same lowest ratio. We're going to learn that's called an empirical formula in some cases, but we do not have to have the simplest ratio like we had to have for ionic compounds. All right. And Molecular formulas also are atoms of one element. So we've already learned about things like O2, which is a diatomic molecule, but technically something like helium, He, it's an atomic symbol, but it's also, you could think of the molecular formula for helium, okay, because you could think of it as a molecule. It's not a compound, it's an element, but if you want to think of it that way, you can. Now, the molecular formula only tells you the amounts of atoms in a molecule, okay, and the types of atoms. It doesn't tell you the structure at all, okay? We have other ways of looking at structure. Okay, so how do we do that? Well, we can represent molecules in different ways. If we look at the ammonia molecule, we can look at the structural formula and show 3 hydrogens bonded here to the nitrogen. Okay, that's a ball, just a stick model. Then we have some things we could have that show how the electron clouds overlap each other. This is called a space-filling molecule. It's the closest to what's probably really happening. This is a perspective drawing. This H is coming out of the board or out of the computer. This one is on the plane of the computer. So we have basically angles of about 105 degrees or so between the nitrogen and the 2 hydrogens in each case. Okay, and then we have ball and sticks molecules that they basically tell you the general location of it, and they'll give you a little bit of the angle perspective. Okay, this doesn't give you as much of the angle perspective. Okay, the arrangement of how the atoms are put together, this is called, obviously, it's a structure, so it's a molecular structure. So carbon dioxide is linear. Okay, there's a carbon here, there's an oxygen on either side. This is space-filling model. Okay, so it's all in a row. This is water. Water is bent a little bit. So here's your oxygen. You kind of got, now I like to call this the Mickey Mouse compound. And they have Mickey Mouse upside down. But if you did it this way, you kind of have this. And there's good old Mickey. So I call water the Mickey Mouse compound. Okay, and then we have more complex compounds that have, this one has carbon, which is the black, gray is the hydrogen, and red is the oxygen. This is ethanol, or alcohol, common grain alcohol. Okay, and it's a little bit more complicated. So the carbons, the first carbon, if we want to write that out, if I want to put it in a structure, that's a little bit easier to see. You'd have C with your 3 H's, like this, and then you'd have another C with an H, an OH, and an H. Okay, so that's how it looks, but since this is a space-filling model, it's I'm going to show you angles and things like that. Okay, just like we can make things out of Tinker Toys, we can think of the different shapes and different things we can do with sticks and balls of the atoms. So we can make lots and lots of compounds and lots of different structures. Okay, acetylsalicylic acid, say that 3 times fast, is the fancy name for aspirin. And there's this molecular formula, C9H8O8. What elements make up acetylsalicylic acid? How many of each type of element are there in a molecule? So I'm going to ask you 2 questions before we do that on Play Pause It, and then you can take that. Okay? So go to Play Pause It. Here comes the question, and we'll be back with the answer. All right, so if we look, we have 9 carbons, 8 hydrogens, and 4 oxygens. Okay, so we have 9 carbons, 8 hydrogens, and 4 oxygens. Okay, there you go. Guess I'll only make 1 question out of that. What representative units define molecular compounds and ionic compounds? Okay, molecular formula for molecular compounds, formula units for ionic compounds. Okay, so if we look, ionic compounds is the formula unit. The molecular compound is the molecule. Okay, so we talked about that last time. So let me just circle those things real quick. Molecules go with molecular or covalent compounds. Ionics are formula units. Okay, now the formula units was the lowest whole number ratio, and there's no such thing as formula units in molecules. Okay, and a molecule is made up of 2 or more atoms that act as a unit. So the thing is, different molecules could be made of the same atoms but different ratios. Okay, and so that's a big difference for covalent compounds. You can't see that in ionic compound because it's a big array. Molecules are single individual compounds. Ionic compounds are a matrix of atoms. Again, there's no such thing as a molecule of sodium. We talked about that. Most of the time what's going to happen is sodium chloride or magnesium chloride. We may say the word molecule, but it really is not correct. As far as physical properties, molecular compounds have usually lower melting and boiling points than ionic compounds. At room temperature, many molecular compounds are gases or liquids at room temperature. They don't have to be solid. Ionic compounds are always formed with a metal and a nonmetal. Most molecular compounds are two or more nonmetals. Okay, so let's look at this. Here's a collection of water molecules. There's one unit or a molecule of water. It looks just like the collection of water molecules. There's no matrix that the water is in. Okay, sodium chloride, on the other hand, comes in the array or matrix of the crystal. We break it down into the simple ratio of 1 to 1 because that's how many we have, and then we make the formula. All right. This will be on play pause it. How is the formula unit of an ionic compound different from a molecule? A molecule is made up of 2 or more atoms that act as a unit. No such discrete unit exists in an ionic compound, which exists as an array of ions. Okay, here's some key points. You might want to take these down in your notes. Definitions, definitely take down in your notes. Some more definitions. And our big idea, bonding and interactions. In molecular compounds, bonding occurs when atoms share electrons. In ionic compounds, bonding occurs when electrons are transferred between atoms. That's it for section 8.1. See you in class.